Okay. Good morning, everyone. Any questions? Okay, so today we're going to move to chapter 11 and section 11.1. Approximating functions by polynomial. Functions by polynomials. Okay. First, let's remember that what's a polynomial? Polynomials are the simple type of functions. So polynomials are like functions of the form, let us say, 2x cubed plus 3x squared plus 5x plus 2. So they are polynomial that only involve power of x and only positive power of x, not positive only, the power of x where the power is an integer. So these are the polynomials. So this is a typical polynomial. So they are really very, very easy type of functions. I mean, this is the easiest we deal with. So if I take a polynomial and I tell you, for example, evaluate a polynomial at any value of 1, for example, we just plug in 1 and you get really a very easy number. So it's really easy to compute those. However, there are functions, most of the functions that we deal with. Let me take f of x equals sine x, which is definitely not a polynomial. Those are not easy functions anymore. Sine, for example, I tell you evaluate sine of 1, you have no idea what sine 1 is unless you pick up your calculator and you evaluate it. So those functions, either though we are so used to them by now, but they are not really easy to evaluate. The idea of approximating function by polynomial is basically a way to take any function, no matter how complicated it is, and you're going to approximate it. It means we're going to view this as a polynomial. That's really nice. So we're going to view the sine function, which is this is fine. We're going to approximate it by a nice polynomial, a simple functions. So that a lot of times, instead of working, even physicists do that a lot, instead of working with the sine, which is a very complicated function, we're gonna do an approximation of it by polynomial, and we can actually work with the polynomial instead of the sine function. Okay, so that's really the idea of approximating function by polynomial. And then, of course, we're going to relate this idea to the notion of series, which is coming later on. But first, we're going to work on approximating those functions. All right. So let us start. We saw in Calculus 1 an approximation. Of course, probably forgot about it. So we're going to talk about first what we know, linear approximation, or Taylor polynomial, of degree 1. So linear approximation of a function f, centered at A. I will read it because I know I goofed. So linear approximation of a function centered at A, or Taylor polynomial of degree 1 of f. At the point A. All right? So linear approximation. What does this mean? And let's remember a little bit calculus 1. Calculus 1, we saw something like that. Suppose you have a function, any function. And we pick a point, any point. Okay, so we're going to call this A, f of A. Okay. Locally, it means when we are near the point, we can approximate a function by a line. Which line? Do you guys have any memory? There is a line that approximates the function near a point.
Was it a tangent line?
Exactly, it was a tangent line. Very good. It's a tangent line. Means locally, near a point, the function and the tangent line are very, very close to one another. So let us remember the equation of the tangent line. Let us remember that. What's the equation of the tangent line? Okay, the slope of the tangent line, the slope is the derivative at A. Okay, that was the slope. And the point on the line is A f of A. So the equation would become y equal, so the equation of the tangent line is y minus f of A, the point slope, is the derivative times x minus A. So that's really the equation of this line. So it means if we rewrite it, this is y equal f of A plus f prime of A x minus A. So that's really the equation of the tangent line. Now look at this. This is actually a polynomial. And sometimes we call it a polynomial in x minus A if you want. But it's just really a simple polynomial. It's a polynomial of degree 1. So this is a polynomial of degree 1. So we're going to write P1 of x.
I have a question.
Yes, of course.
What's in between f prime of A over x minus A? I mean, what is that, like a plus,
That's
minus?
a multiplication.
Oh, okay.
Yeah, we're multiplying. It's the point slope form of the equation of a line.
All right.
All right. So we're going to set P1 of x to be f of A. It means, in other words, P1 of x is the function whose graph is the tangent line. So P1 is the function whose graph is the tangent line. Okay, that's really P1. P1 is the function whose graph is the tangent line. So P1 is called Taylor polynomial. So that's P1, Taylor polynomial of degree 1 of degree 1. So that's a polynomial basically that's gonna approximate the function locally near the point A f of A. So now, and we work with this a little bit in 163, and the idea is that we're approximating a function by a line. So this is a good approximation. Not great, but good. So the question is, can we do better? Can we approximate the function by better polynomial? So now we're going to approximate the function by a parabola, and which is usually a polynomial of degree 2, something like that, a parabola, something that curve like the function. And the question is, what is the polynomial that has the property that it actually not only share the same tangent line, but curve exactly like the function? It means if the function is concave down, it will be concave down, concave up, concave up. So part 2 is quadratic approximation of f centered at A, or Taylor polynomial of degree 2. So quadratic, because we wanted to approximated by polynomial of degree 2. So quadratic approximation of f with centered at 2, with center at A, or Taylor polynomial of degree 2. Taylor polynomial of degree 2. Okay. So first I will give you the formula for it, and then I tell you a little bit about the property of this formula, why it's a good approximation. So P2 of x, that's going to be the Taylor polynomial of degree 2, is given by the following. f of a. So the first part is going to be exactly like the first degree Taylor polynomial. So this is the tangent of the equation of the line, but we're going to add a quadratic term, which is going to be the second derivative at a, first derivative, second derivative, divided by the 2 factorial, which is 1 times 2, times x minus a squared. So that's will be what we call Taylor polynomial of degree 2. Now, let's see what's the property of it, of this. So this is my function f of x. That's a point A right there. And this is the first degree Taylor polynomial. That's really the tangent line. Okay. Now, P2, watch which property it has. If I evaluate this polynomial at A, what do I get? It means if I plug in A for x in this expression, what do I get? If I plug in A in here, I plug in A in here, I get f of A plus 0 plus 0. So this polynomial will have at A the same value as my function itself. Now, something else this polynomial has. I'm going to evaluate. I know it's a little bit abstract, but that's the last abstract thing I will do. Let's see what's the derivative of this polynomial. Let's see what is derivative. F of A is a constant. It's a 0. Okay, plus. F prime of A, this is a constant, times the derivative of x minus A is just 1. Plus. This is a constant because that's A is a fixed number, so that's fixed. The derivative of x minus A squared is 2 times x minus A times the derivative of the inside, which is 1. So this is this polynomial at A takes the value A. Now, the derivative at A means that's a function. Its derivative equal. If I plug in A in here, I will get f prime of A, and I will get a 0. Okay, so this polynomial that I'm giving you the formula for it, its derivative at A is the same as the derivative of f at A. Means when we are going to grab this polynomial, it takes the same value of A here, and it shares the same derivative. It means that this line is tangent. The line which is tangent to the function is tangent also to this polynomial. So the polynomial cannot look like that because that's the tangent line to it. So it's going to be very actually close to the function. It's going to be something around the function, Now, the last piece, what's the second derivative of this polynomial at x? The second derivative. That's 0. That's a 0. F double prime of A is a constant times 2. Derivative of x minus A is 1. So I simplify those. It means the second derivative of the polynomial is constant. It's equal to the second derivative at A. So what does this mean? What does this function, which is share with the original f? So what does this polynomial share with f?
I have a question.
Yes.
So is p to the second power, I mean not second power, but p
Second derivative, yeah.
Second derivative, f second derivative of A also?
Yes. Yeah.
Okay, so x and A are the same thing.
No, sorry. A is fixed. X is a variable.
I mean, when you do p to the double prime of x
they
and
are
p to the double prime of A.
Because yes, why? Because the second derivative is constant, is equal f double prime of a. So no matter what you put here, you're gonna have f double prime of a.
Okay.
Chris, did you get it? It's not the
Yes.
case here. Here, x is variable. So when I put x, a for x, this give me a 0, leave me with that. It's only the second derivative, which is constant, which is equal f double prime of a. It doesn't depend on x.
All right.
Okay, now keep going. So how is the polynomial look like? It has the same value as the function. It has the same derivative, it means share the tangent line. It has the same second derivative. What does this mean? What does the second derivative tells me about the function? Let's see if you guys remember. The second derivative measures what about the function?
It measures the slope of the first derivative.
Yes, but what does it tell me for the function? That's absolutely a correct answer. But what
Doesn't
does
it say concave up or concave down?
Exactly. It tells me if it's concave up or concave down. That's what it measured. So if the polynomial of degree 2 have the same second derivative, means if the function is concave up, it will be concave up. If the function concave down, it will be concave down. So this polynomial will share the same concavity as the function itself. So graphically, how's the polynomial look like? The polynomial cannot look like that because it have the same concavity as the function. What the polynomial is gonna do is gonna hug the function more. So basically hug it more like this. That's how it's gonna look like. So it's gonna give me a better approximation of the function, better than the tangent line. So the tangent line go like, so that's my function. That's the tangent line. The polynomial that I gave you, its formula that we're going to work with it in a second, have the same concavity of the function. So it's going to coincide with the function over a larger interval. So it's going to look something like that. That's the function. That's my polynomial. It's going to really hug the function more. As a result, it's going to approximate the function on a larger interval. So that's the second degree Taylor polynomial. So let us say just a small application to that, and then I'm gonna dump on you basically what we're gonna call Taylor polynomial of degree 3. It means another polynomial which will actually be closer to the function than even the second degree polynomial. So the idea is to basically approximate the function more and more by polynomial. So before I do this, let me make a small exercise just to practice this. So I'm going to say let f of x be equal. Let f of x equal, let us say the square root of x. Okay, very example. Question is, find the linear approximation. That's another word of saying find the Taylor polynomial of degree 1. Find the linear approximation of f at the point a equal to 1. Means we're going to approximate the function square root of x by its tangent line at 1. So this is right here, this is a 1. Basically, the linear approximation means find the equation of the tangent line. All right, so this is f of x. To find the equation of the tangent line, I need the derivative for sure. So f prime is a half x to the minus a half. Now I need the tangent, I need the slope. So I need f prime of 1 equal a half. So the linear approximation that we're going to start writing it as P1 is equal to the value of the function at 1 plus f prime of 1 x minus 1. So P1 of x is f of 1 is 1. So it's 1 plus a half times x minus 1. That's the linear approximation. It means that near 1, the value of the square root of x are very close to the value obtained by this polynomial. Now we're going to do the quadratic to find either quadratic or the Taylor polynomial of degree 2. Find the quadratic approximation of the same function, f at a equal to 1. Okay, let us remember the formula. So P2 of x is f at a at 1 plus f prime at 1, x minus a, plus f double prime at 1, x minus a square, over 2 factorial times x minus 1 square. Okay? All right. So to evaluate this, I need f prime of 1, and I need the second derivative, not only the first. So let us here. So the first derivative, f of x equal square root of x, x to the power a half. So f of 1 is 1. We got it from before. Yes.
Isn't the at the end of the P2 equation, isn't it x minus a?
Yes, absolutely. But what's a in my particular
Oh,
problem?
1. Sorry about that.
No problem. F prime of x is a half, x to the half minus 1. I know that I did it, but it's just going to build the habit of doing that. And the second derivative is a half times minus a half, minus 1 over 4, x to the power minus a half minus 1, minus 3 half. It means that the second derivative at 1 is minus 1 over 4. So my second degree Taylor polynomial, or the quadratic, is the following polynomial. P2 of x equals f of 1, which is a 1, plus a half x minus 1 minus 2 factorial, 1 over 4 times 2 factorial, x minus 1 squared. So of course, nobody liked that. So the second degree Taylor polynomial is 1 plus a half x minus 1 minus 1/4 over 2 factorial, if we use our properties of fraction, minus 1 over 8 x minus 1 squared. Okay. So that's my second degree Taylor polynomial, which is going to actually approximate the square root of x better than before. So part C here, we're going to do the following. Okay, part C. Approximate square root of 1.5 using a Taylor polynomial of degree 1, or the linear approximation using Taylor polynomial of degree 1. And then we're going to do it using the Taylor polynomial of degree 2. Means using the quadratic approximation. Okay, so what do they mean by that? What do they mean by that? Right. Let's note that square root of 1.5 is nothing more than the value of the function at 1.5, because f of x equal the square root of x. It means that square root of 1.5 is the value of the function. Now, how are we going to do the approximation? The approximation is simply the idea of plug in 1.5 in the expression of the polynomial. And the values are supposed to be close to the actual value of the square root of 1.5. So let me write this down. Basically, I want to evaluate the polynomial at 1.5. So instead of evaluating the function, which is really hard to do, I'm going to evaluate the polynomial. What do I get? 1 plus a half times. I just plug it in this expression, 1.5 minus 1. It means 1 plus a half times 0.5. Okay, I'm just plugging in. So this will give me 0.5 divided by 2. So it's going to give me 0.25, 1.25. So I'm trying to use those polynomials to approximate the actual value. Now, B, I'm going to use the second degree Taylor polynomial. This is going to give me 1 plus. So the second degree is right there. Plus a half, 1.5 minus 1, minus 1 over 8, 1.5 minus 1 squared. So I plug in 1.5 for x. And now I do the math. So this would give me 1 plus a half times 0.5 minus 1 over 8 times 0.5 squared. Now I plug in into my calculator because none of us can do that in their mind. We will get 1.21875. Okay. Now let us see what's the actual value of the square root of 1.5. It means the value we pick up from our calculator and see how good our approximation are. So the actual value of the square root of 1.5, it means the one I pick up from their calculator because they have a very good algorithm to approximate that. So if I pick it up, I will get 1.2247 and 4. Okay, so that's really the actual value, and this is really my approximate value. So if I use the tangent line, I get the 1.25, which is not really bad. I mean, it's not great either, but it's not bad. And then if I use the second degree, I get actually an even better approximation. So that's really the idea. It's really is the idea of viewing square root of x as this polynomial. Now, can we do better than that? Can we do better than that? And this is where we have to dump a theorem at you. And we can talk about, are you guys done? And we can start talking about Taylor polynomial of any degree. Means we did degree 1, degree 2, because I can explain the geometry about it. But then there is the idea of Taylor polynomial of any degrees. And the idea that the higher the degree we will be taking, the better the approximation. So you guys write it down and then we'll stop. So let f be a function. A function with f prime, f double prime, and the nth derivative, all defined at the point A. So A is going to be fixed in my problem. A is going to be the base point, which is going to be fixed. Then, the nth order Taylor polynomial of f. So A is fixed. That's fixed. That's not the variable. X will be my variable. The nth order Taylor polynomial of f with its center at A is given by.
Can I go back up a little bit?
Absolutely.
Thank you.
Because it's absolutely right. Now this is f prime, f double prime, the third derivative, and this means the nth derivative. Okay, so when you put n between parentheses, we mean by that the nth derivative. So the nth order Taylor polynomial of f with its center at A is given by. Okay, let's see how it's built. This is the first degree Taylor polynomial. That's the tangent line. F of A plus f prime of A times x minus A. Then you add the quadratic term, which is going to give me the quadratic approximation. And then we add the third term, which is going to give me what we call the cubic approximation. So it's the third derivative divided by 3 factorial, x minus A to the power 3. So that's really what the pattern is. The second derivative over 2 factorial, x minus A squared. the third derivative at a over 3 factorial, x minus a to the power 3, plus etc. The nth derivative at a over n factorial, x minus a to the power n. So we're going to call this the Taylor polynomial of degree n. And the idea is that 2 approximate the polynomial fair enough. If I take the cubic approximation, I get closer to the function, and so on and so forth. And in sigma notation, this is going to be given by this expression in sigma notation. Because in sigma notation, the general term have the form: the nth derivative, the kth derivative at a over k factorial, x minus a to the power k. And the sum is from 0 to n. Okay. We're going to call this Taylor polynomial, as I said, its goal to actually hug the function, approximate the function. I stop right there. On Monday, of course, we're going to work with it. And your exam number 3 is, as you probably most of you know, is next Friday. The review will be out by tomorrow. Okay, get started with the quiz.